We are having some technical issues with the mic, but hopefully it's going to work now. So I was saying that I'm Jingxi, and I'm very excited to be here to give a guest lecture on what we have been working on in the lab. So normally in previous years, Mateo will do the introduction, but he's not here today, but trust me, I'm invited. So let me introduce myself. I'm Jingxi, and I'm a fourth-year PhD student in Mateo's lab. I do work in two directions. My first direction is tactile sensing for robotic manipulation, and my second research direction is what we're going to talk about today. We developed I work on the machine learning aspect of the My Hand project, where we develop a hand orthosis to help stroke subject regain functional usage of their hand. Okay, so so the goal of this lecture is I know that you guys have been learning about the machine learning algorithms in this class, and you have done homework assignments on like problems, like navigation. I think in the future you will do forward dynamics. But the world is less structured, and it's not a toy problem anymore. So I just want to, hopefully after this lecture, you will be more confident about developing a robot learning application, and what are the possible problems that you will encounter in doing that, and what are the tips that you can keep in mind to solve these problems. Okay, so without further ado, let's get started. So before I start, I should say the work that we're going to talk about today is in collaboration with a group of fantastic people, including mechanical engineering PhD students who developed the hardware, and also therapists and doctors from the medical school. And in case you don't know, like Columbia does have a great medical school, and it's in Upper North. That's where all the experiments took place. Okay, so feel free to stop me for any questions. So the motivation is there are 800,000 people having stroke in a year in the US, and only 77% of these patients will exhibit impairment in the upper limb, and less than half of them recover full function. So the goal of this project is to help stroke subjects reuse their hands, regain functional usage of their hand. So a lot of the daily tasks that you and I, we took for granted is very hard for the stroke subject. And this is an example. This is a stroke subject trying to do a pick and place. Obviously, it's impossible for her to do that. So what we do is we develop this hardware, this device. It's an Orthosis exoskeleton device that has EMG armband as our sensor. So the EMG is short for electromyography. It's basically the muscle signals of your muscle activities, and this armband is able to measure the electrical signals of these activities. So this is the sensor that we are using, the EMG armband. And our device also has a motor, and the motor is attached to some strings or tendons. And if the motor moves, it can pull the strings and then help the stroke subjects open their hand. And if the motor releases the string, the subjects can use their own strength to close their hands. So the population we study in this work is the stroke subjects that lose their ability to open their hand out of a closed fist, but they still have their own strength to close their hands. So that's our target population. So the end goal of this project is to develop machine learning algorithms that read from this EMG armband, read the EMG signals, and predict the intent of the patient. So if the algorithm thinks the patient wants to open their hand, the motor moves and pulls the strings and help them open their hand. If the algorithm thinks the patient wants to close their hand, it will send a close command to the motor releases the string, and then the patient can use their own strength to close their hand. So this is the goal. This is what we want to do. We want to do inter-inferral using the EMG signals with machine learning. Cool. Right. So whenever a person approaches me with a robot learning application that they want to develop, I always think from two aspects. And the first aspect is data. Like, what data is available? What data can we collect? How can we collect them? And how are we going to process them? So that's the first aspect. The second aspect is the algorithm. So what specific classification algorithms are we going to use to solve this problem? Right. This is what I call the two pillars of a machine learning application. So let's look at this problem from these two aspects. First, from a data aspect, what features are available for us to use to solve this machine learning problem? So obviously, we know that we have the EMG armband. So the EMG armband, it has 8 electrodes surrounding the forearm. So it's able to output 8-channel EMG signals at 100 hertz. So this is a demonstration of me wearing the armband. You can see when I open my hand, there's a change in the EMG signal patterns. And when I close, there's a different signal patterns. But it's worth noting that I'm a healthy subject, but these will be much more subtle, if any, on stroke subject. So that will be the challenge. Because you can see my signal reaches around like 1/1500 sometimes, but on stroke subject, it's never as intense as this. So this is the feature we're going to use. And then how many classes should we distinguish between? And this is an easy one, because for our case right now, we are distinguishing between open and closed. So we are solving a 2-class classification problem. And how are we collecting them? So we'll develop a GUI on the laptop, and we'll bring the laptop to the hospital. We schedule patient sessions with the subjects. And then what we're going to do is we give out verbal cues. We'll tell them now try to open or try to close. And at the same time, we are recording the EMG signals. And the way we label the data is by when we give out the verbal cue, we will click on the GUI to set the ground truth label so that we label all the data collected during this time labeled as open or closed. And then the next question is, how are we going to pre-process the data? Then I want to give out the first tip I have. So throughout the lectures, I'm going to give out ideas that I think is important, which is going to be highlighted in this red rectangle. So always pre-process and clean your data set. So at least standardize or normalize them. So in machine learning, like a lot of times, like your features, when you have a lot of features, and different feature has a different meaning, and they often come in different scale. For example, height and weight are two different things, and they come in different scale. And it's really, really important for you to make sure they are scaled to the same range, so that it's going to make the machine learning algorithm it's going to help them to learn, right? So does anyone know what is the difference between standardization and normalization? No? Did Mate cover this? Yes?
Normalization is making the data with, I think, a 0, making it go from 0 to 1. I think standardization is when you make it 0 mean and standard, 1 unit of variance.
Exactly, yeah, you're absolutely right. So standardization is making the data follow a normal distribution with a mean 0 and standard deviation 1. And normalization is using the minimum and maximum value from the data set to convert the data in the scale of 0 to 1. Okay, and this is important. So for our application, we have 8-channel EMG signals. Each channel, so each feature is a channel of EMG signals. They don't follow a different scale, but we still do standardization because the network will have the algorithm will have an easier job if it sees like small floating numbers in a good range, 0 to 1, compared to like an integer that goes up to 1500. So we do standardization, and the question next is how much data do we need to solve the problem? Of course, like for any machine learning applications, the more the better. But in our case, I want to point out that we are very limited by the real-life constraint because it's very, very hard to collect enough data on stroke subjects. So we have to consider that. We have to keep that in mind. And in fact, this is going to be a main challenge throughout the whole line of research work, which is we need to handle the data scarcity. Right, so that's the data side. And then now, if you look at the algorithm side, we need to pick an algorithm, right? So here I list out for popular methods, candidates that we are considering for training an interinferral classifier for the patients. So there are SVM. So SVM is support vector machine. It's optimizing the decision boundary such that the margin between the two classes are maximized. And LDA is for linear discriminant analysis, which is feeding Gaussian distributions for different classes. And then random RF is short for random forest, which is an ensemble of decision trees. And then neural network, last but not least, probably the most popular method in the list. Has Mate covered all of this? Not at all? Some. Which one is not covered?
I don't think we did LDA.
Okay, cool. Okay, so these are the algorithms that we are considering for this problem, and also we also the things that we consider for these algorithms are the number of parameters to learn, the time to train such algorithm, and the third one is interesting, updating. So this is not particularly interesting for now, but it will be useful in the second stage. So updating means whether you can adapt this model to a new sample without like retraining on the whole data set again. So updating is whether you can adapt in the online or in an online fashion. And the last thing we consider is how much training data do you need to realize the full potential of an algorithm, right? So let's start with SVM. So SVM, obviously, you are learning a linear decision boundary, which has very few parameters to learn, which is good. But SVM takes much longer to train compared to LDA and the random forest. And this is because when you optimize the decision boundary, you need to keep a kernel matrix of all the pairwise dot products of all the data samples. So your kernel matrix will grow quadratically with the number of data samples. So when you have more data, it's going to slow down SVM a lot. So that's why I say for SVM, less training data is better. Otherwise, it's going to slow down a lot. SVM is really good for when you have a small data set, a small number of data samples, but each data sample has a lot of features. But it's not good for when you have a large data set, but each data sample only has a few features. Right? So that's SVM. And every time if you want to adapt to a new sample, you have to add this new sample to your entire data set and then retrain, re-optimize the decision boundary again. So it's not good for updating. Okay, feel free to stop me for questions if there's anything unclear. So the second one is LDA, which is also just a few parameters to learn, and it trains much faster. And you can update LDA because it actually has a closed form solution for updating your Gaussian distribution. Because effectively, you are feeding Gaussian distributions to different classes, and it has a closed form solution when a new sample arrives. So it's good for updating. And then it can work both with a small amount of training data, but also the more data you give to LDA, it doesn't slow down the training a lot. So the number of training data samples is flexible. And this is the same for random forest. We are just learning some boundary threshold, like thresholds for the decision tree, and it trains fast. Again, it's not able to adapt to a new sample online, and the number of trained data we need is flexible. So the last one, neural network, and it's famously known for being data thirsty. It needs a lot of data to realize its full potential. So, and it also has infinite number of parameters to learn. It has, if you have a giant network, then you have millions of parameters to learn. And the more data, the better. You can also fine-tune a network on a new data sample online. You can run a few gradient descent steps and then backpropagate to update your network parameters. So that's the characteristics that we are considering for these four classifiers, and then we need to think which one works best for our application. So a question for you guys, food for thought. Which one would you choose if you're gonna do this inter-inferral thing? Any ideas? Yes?
Maybe the random forest.
Why do you think so?
Because given that you have like what eight features, it's a good number to start with. It's less than 15, and you don't have too much data because with neural networks you get a large amount of data. With random forest you don't need too much. I mean, more data is better, but it doesn't require a large amount of data. The updating might be a problem, but I think there is a warm start parameter with that as well. So and they tend to perform well for most tasks where the data isn't too much.
So what specifically do you think random forest is better than LDA? Why do you think it's better than LDA?
I'm not familiar with the LDA.
Okay. That's also a very valid reason. Like I'm not familiar with the algorithm, so I choose the other one. Any other ideas? Yes?
The LDA.
LDA?
It looks like it checks all the boxes that you have for this particular task. And
right.
Especially being updating if you have like sparse data coming in, probably whenever you have access to a stroke patient. So being able to update is going to be important.
Nice. That's a valid point. Yeah. So yeah, it looks like LDA and random forest are the most tempting solutions. In fact, I think both of you are right. For this work right now, we're going to talk about, we actually choose random forest. But then for the next work, in the second stage of the lecture, we're going to talk about work that we use LDA. So, okay, so of course, before we make the call, we have to evaluate like the performance. So how well do these algorithms work on our data set? So we do a quick pilot test on the data set, the offline data set we collected, and then this is the results. So we present the accuracy and also the positive predictive values, which is the proportion of positive predictions which is in fact positive, and the negative predictive values, which is the negative predictions which are in fact negative. So you can see from these results here, like we don't have a balanced data set. Like 81% of our data set is negative samples, which means close. And obviously, SVM and neural network are not learning very well because even though they have a decent accuracy, they are basically predicting everything as negative. So that's how they reach such accuracy. But this is not what we want. So based on these results and also the characteristic we showed before, we decide to rule them out. So now we are left with LDA and random forest. So the reason why we choose random forest is because we have a slightly higher accuracy and a more balanced prediction between positive values and negative values. Okay, so we choose our classification algorithm. Now we want to fine-tune we want to tune the hyperparameters. So hyperparameters are the parameters that specify the learning process but are not learned and are not part of the model. So we will run a grid search on all these possible parameters, hyperparameters for random forest. I won't go into details here. You can look up the documentation for random forest. So basically, we compare every pairs of combination, and then the best combination we found is highlighted in red. Okay, so after tuning this, we don't have a much gain in accuracy. We have a more balanced prediction. However, interestingly, like it takes much longer to train after we fine-tune our classification algorithm. It's like 1 order of magnitude longer to train. So this is interesting because oftentimes, like real-world constraints will affect how we select our hyperparameters. And in this case, specifically, random forest, the most important hyperparameter for random forest is the number of estimators. The number of estimators is basically the number of trees in your forest. And then we can see that when we go from 10 trees to 100 trees, we gain quite a few percentage gains on accuracy. It also takes longer to predict. This is the inference time when we are using the classifier. So it takes longer to predict, but the gain is also what we want as well. But if we go further from 100 to 1200, we don't gain much. We don't gain accuracy improvement at all, and it takes much longer to train. So we decide to go with the 100 estimator RF version, so that we strike the right balance between a good accuracy and also fast enough time to inference to intend inferral on the stroke subjects. So we decide to use this configuration. Yeah, question?
What was the size of the training set?
Right. Yeah, I forgot to say. So when we are collecting the data, it's around like 5 to 10 minutes of EMG signals from the patient, and I think that's 50K data samples, which is still small compared to like vision or language. Yeah. Cool. Good question. So we decided to go with the configuration in the middle. But it turns out that this is not working at all. And even though we have a 90% accuracy, but when we plot the qualitative results, that's what's happening. It turns out that our prediction oscillates a lot. You can see this plot, the x-axis is time, y-axis is the intent, the blue line is the ground truth, and the red lines are the prediction. So you can see basically our model is switching between open and close too frequently, even though it achieves overall around 90% accuracy. And this is not what we want at all, because if this translates to the real hardware, that means there are a lot of open and closed motions. So the lesson we learn here is the success metrics are only good if they are relevant to your application. So in order to fix this, the solution we came up is we add a median filter. So we add a median filter, which is like a sliding window of size 20, and we will use the median value of the 20 time steps as the value for the whole window. So doing it this way, we are able to smooth out some of the spikes, and this is what it looks like between this time range. Between this time range, and if we zoom out, that's what happens after we apply the median filter. It looks much better than before. The oscillation is removed, and we actually gain some accuracy as well, so which is good. Another thing we can do is we can alter the threshold. So we are also using thresholding to smooth out the spikes. So what is thresholding? So thresholding is you only send a command to the motor if your predicted probability is over a threshold. So for example, like if you have a threshold of 0.8, which is a predefined threshold, and at a certain time step you are predicting 0.6 as open, 0.4 as closed, even though the prediction is open, you don't send a command. You only send a command if your open probability is over the predefined threshold. In this case, it's not over the threshold, so you remain the previous state. So you don't change the state. So like all these methods, the thresholding and also the median filtering are all, we as humans, we are injecting priors like into the system, because we know that stroke patients, they don't open and close in high frequency, right? They tend to close and open in a much lower frequency than what the model predicts. So this is us injecting our own prior knowledge into the system. So after thresholding, and the thresholding is also something that is varying between individuals and individuals. For different patients, you might need to tune the threshold differently, because for some patients, they have some residual or voluntarily open motion. So you can set the threshold for open to be higher. And if it's really hard for them to do any open motion at all, you can set the threshold for open to be lower, so that it's easier for us to send a command to the device to help them open their hand. So with all these tricks, we are able to do this well on an offline data set. And it looks great, right? And again, with these tricks, we almost reach 95% accuracy. So it looks like it works, but unfortunately, it is actually not. And why is that? Because if it only works offline, it is not really working. So up to now, like all we have been doing is we go to the hospital or collect a data set while doing a lot of offline analysis on this data set. But then if we actually run this algorithm on the device in the hospital, it's not working. And why is it not working? This is because when the patient is using the device, their arm tends to move, and they will move to a different position than what is recorded in the training set. Remember that when we were collecting data, what we are asking the patient to relax their arm on the table, and the device is not engaged. The motor is not moving. But when the patient is doing functional pick and place, they're going to move their arm around, right? And the motor is going to move, so their hand is going to interact with the motor. So this is the EMG signals when their arm is relaxed on the table and device is turned off. You see this pattern and this pattern for close. And when they start to raise their arm above table, you see a very different pattern. And because your algorithm hasn't seen this pattern before, it's going to make a lot of mistakes on these data patterns. And again, like when the motor starts moving, when the motor is interacting with the patient, you see another different patterns for open and close. So they together will make your algorithm fail. And this is a quantitative visualization of the problem. It's trained on this condition, and the green dashed line indicates a change in condition. And when the patient starts to move their arm, or like the motor starts moving, like you can see, the algorithm fails drastically. And when the motor is engaged, it almost never works. So the lesson we learn here is when you train an algorithm and you have super high training accuracy, but it never works on the test data set, the thing you can think about is, one, is it overfitting on the training set? Second, if there's a big mismatch between your training data set distribution and your testing data set distribution. So in this case, there is a big mismatch between the train and test. You are expecting the algorithm to work on some conditions or distributions that has never been recorded in the training set. But we have a quick fix for this. What we are doing is we alter the training protocol. So instead of just collecting data with one condition, now we collect data on all possible conditions. We collect data on arm off table, device on, and we also collect data on arm off table, device off. This is not the best solution, but it's able to help us resolve this problem quickly. So finally, with the expanded training data set, we're able to make the device work. And this is what the plot looks like. And we bring this product or the algorithm into the hospital to test on the real patient. And now the patient, she's able to complement pick and place motion, which she was never able to do before. This is good, but at the same time, there are some problems with this. You can see there's clearly some delay, and she has to try a couple of times before the device actually open or close as she intends. But we're getting there. Cool, so are we done? Yes, because we have enough contribution to publish a paper. This is a big part of your PhD thing, right? It makes you feel better. So all the things that I've talked about is wrapped up in this paper. You can check it out on my website or the lab website. But at the same time, we are still far from our end goal, right? Our end goal is to develop such a system that we can deploy in the real world for stroke patients. Clearly, we're not there yet. So what are the big problems? So the big problem is from the simple and quick fix that we had before. What we are doing is we are collecting data on all the possible conditions, which brings a lot of burden on the stroke subject. And stroke subjects, they are easily tired and they easily get fatigued. So this is not what we want. But again, so a key point here is training data is always expensive to collect, and the less data your algorithm needs, the more generalizable it is to real applications. And so this is generally true for all machine learning and robotic problems, but this is particularly true for our application, because collecting human data on disabled body subjects is basically the problem of data scarcity to the extreme. And if there's any application that needs to work with less data, this is the application. So we don't want to collect so much data to put so much burden on the patient. But we're not doing anything wrong here. We are doing the 2 stages of development. We try to push to a prototype first. Even though it's not perfect, now in the second stage, what we're going to do is we're going to polish our system. But it's always good to have a working demo to make your advisor happy fast, right? You can't think about all the possible problems beforehand. Okay, so in the remaining of this lecture, I'm going to talk about what we do to improve the system to solve the problem of too much burden on data collection. When does the lecture end? What? 2:15? 2:25. Okay. Right, so it turns out that the problem that we have been talking about, the mismatch between the training set and test set, actually has a technical term, which is called by people in the literature concept drift. The concept drift is the change of data distribution. Again, I'm showing you guys the EMG signals as the patient moves their arm and the motor is on or off. You can see big change in the EMG signal pattern when the arm changes position, etc. And concept drift can not only come from arm position or motor state. It can also come from device migration as the patient uses the device, or it can come from just the patient getting fatigued. So the goal of the second half of this lecture is, can we handle this problem without collecting data under all possible conditions? And sometimes you can't address the concept drift caused by fatigue by collecting more data, right? You can't tire them out and then collect data just in case they get fatigued in the future. So what we're gonna do, right? So there are a lot of ideas we can try, but let's take a step back to look at the 2 aspects that we talked about in the beginning. What can we improve on the data set, and what can we improve on the algorithm side of this problem? So it turns out that there are a few things we can do. We can add to the data aspect. What we did is we introduced one more class, which is relax. Before, we only have open and close labels, but intuitively, there should be a relaxed state, right? In a relaxed state, there should be moments where the patients they don't want to do anything. They don't want to open. They don't want to close either. So in this case, they should just relax. And this also gives the patient more time to just be relaxed and not engage their muscles all the time. It helps relieve their spasticity and the tension in their muscles. Cool. So that's the first thing we did. And the second thing we did is we are adding a lot more sensing modalities. Before, we only have the EMG armband, but now we are adding motor position encoder, which gives us the motor state as another data modality. We also add IMU sensors. So the IMU sensor can give us the position of the index finger compared to the reference IMU. We also add a pressure sensor to the thumb, which can measure how much pressure the patient is pressing the device. So adding more sensing modalities give us more room to play with data, and hopefully they can make the algorithm more robust. So that's what we did for the data. And on the algorithmically, we are borrowing ideas from the semi-supervised learning literature. So semi-supervised learning is basically the idea that you train both on unlabeled data and labeled data. So it depends on the heuristic that you use to label the unlabeled data. And the idea here is we only collect a small initial data set. In this case, we only collect for arm off table and device on. And then we train an initial algorithm and we start to load the algorithm on the device and the patient starts using the device. And as the patient starts using the device, the algorithm, we are expecting the algorithm to update themselves with the new unlabeled data that is collected when the patient is using the device. So that's the high-level idea. So because we changed our strategy, we have to revisit our list of candidates. And because a lot of the conclusion we draw before might not hold true anymore because of the change to semi-supervised learning. So in this case, what we gonna care a lot is actually whether we can update the thing, because we're expecting the algorithm to update themselves in an online fashion with the new stream of data, right? So because of this, we immediately rule out random forest and SVM because they are not able to adapt to a new data sample. So now we are left with LDA and neural network. And the choice seems obvious because the problem of neural network being data thirsty does not change. If any, it only gets worse because now we try to work with even smaller initial data set, right? And also, the speed matters because now we want the algorithm to work in an online fashion. The problem that neural network takes a longer time to train is problematic. It's gonna do a lot of delay on the device while the patient is using the device. So we eventually go with LDA. Right. So this is the overall algorithm that we are using. So our semi-supervised algorithm is discriminant based. So I mean the core of any semi-supervised learning algorithm is the heart and soul is basically how do you label the unlabeled data. And the way we label the unlabeled data is based on discriminant. So before, we only have one classifier, but now we have an ensemble of classifiers. So we have a lot of classifiers in our ensemble. And the key point here is each classifier is using a randomly sampled subset of the data modalities. Just remind you guys, right now we have more modalities than just EMG signals. We added much more sensing modalities, and each classifier is using a randomly sampled subset of these modalities. And the intuition behind this is when we have multi-modality data, when concept drift happens, it's possible that some modalities will be robust to this concept drift, while some are not. So that we can use the classifiers with the robust modalities to help the classifiers with the less robust modalities. So that's the idea. Questions? Okay. So when a new data sample arrives, so we train an initial algorithm and then we start to use the device on the subject. And then the unlabeled data starts to arrive, right? And when a new data sample arrives that is not labeled, we'll feed this data sample into all the classifiers in the ensemble. And each classifier will have their own predicted probability distribution over close, open, and relax. And what we do is we calculate the entropy for this probability distribution. And then the entropy is used as an indicator of confidence. So if you have a smaller entropy, that means your model is confident. And if, for example, like the LDA 1 and 3 is confident because they have low entropy. And if you have a large entropy, that means your classifiers are not confident. And if the confident classifiers agree on the predicted label of this data sample, then we will label this unlabeled data sample using the label that they agreed on. So that's how we generate labels for unlabeled data. And we will add this newly labeled data into the data buffer of those unconfident classifiers. So we have a data buffer for each classifier. And when you have accumulated enough data in the data buffer, we will run an update. We'll use the newly collected labeled data to update those classifiers that are not confident. So that's how we achieve the information transfer between confident classifiers and unconfident classifiers. Right. So using the semi-supervised learning algorithm, obviously we can do better than the baseline. So here we compare on the top row, the baseline, where the model is only trained on condition number 3, arm off-table motor on, but tested on all 3 conditions. And the bottom row is our method. It's also trained only on the first condition. This condition, but it's doing the self-online updating on the other testing conditions. So the baseline is able to do an okay job for the condition that it's trained on, but it fails more drastically when testing on another condition. But ours remain a relatively high accuracy compared to the baseline, and this thanks to the semi-supervised online updates. And again, if it only works on offline data set, it doesn't mean that it works. So we bring the algorithm and device to the hospital, and we test on the real subject. So for the first subject, it's able to complete 7 times of pick and place in a minute. So this is 4 times speed up. So we can see that the algorithm works more responsive than before, and it also, according to the patient, is more robust. And then we evaluate on another subject. So interestingly, for this subject, in the beginning, there are some jerky open and close motions. But in the end, it goes away. We attribute this also to the online updates. He's also able to complete 7 pick and place in 1 minute. Okay, so yeah, question.
Is it learning while inferencing?
What?
Is it learning while inferencing? Like during testing, is it learning at that time as well?
Yeah. So this is our algorithm on the fly, on the device. So yeah, we collect the initial data set following the same protocol, and then we start to use the device. And as the patient is using the device, the algorithm is still updating itself with the unlabeled data. Any more questions? Yes?
Was there anything special you guys did to make sure that it was really responsive between the sensor input and actually driving the motor, or was it pretty standard procedure? It looks very responsive to their when they want to drive it and when the motor is actually actuated.
Yeah. I think there has to be a lot of work to achieve this, both on the hardware side and the software side. So on the hardware side, you have to make sure your ROS packages are communicating well, and they are sending messages at fast enough frequency. And on the software side, we have to make sure that the inference time of the algorithm is fast enough. And that's why when we talk about the choice of candidate classification algorithms, we rule out neural network, because the inference time for neural network is much longer than LDA. So then you will see much longer delay. But this is using LDA. We intentionally choose LDA because it's fast. Any more questions? Okay. So let's move on. Actually, there's nothing more to move on. Yeah, so we have a new paper, and all the stuff I talked in the second stage, how we polish the algorithm is in this paper, and you can check it out. And we are still not achieving what we want because there are always open questions, right? And there are future work. So for example, like what if the patient take off the device and put it back on after a week? Then you will see more concept drift. And actually, this is what we call intersession drift. What we have been dealing with is concept drift within a single session. But when the patient take off and put it back on, that's cross-session concept drift, which is a harder problem. And also, can you develop an algorithm that is invariant to the EMG sensor position, right? What if you just rotate the EMG sensor on the forearm, and then can you make your algorithm not fail? And there are also work on the hardware side, because we still need to make this a take-home device where the patient can put them on themselves. Because right now, like we always need a professional occupational therapist to be there to help them do the job. And there are a lot of open questions, but I think that's enough for today. And thank you a lot for your attention. And I'm open to questions, ideas. Yeah.
The first point you mentioned that intra-session concept drift. Why is that? Like for the same patient, suppose you do it after a week, what would change?
A lot will change. So subject, their state, their spasticity. Like spasticity is the resistance when you try to open their hand, right? This will change after like in a week or something, and it's hard to predict what the change will be. And also, if you take off the device and put it back on, it's hard for you to align the sensor exactly as before. So that's also a challenge thing to do. Yeah, good question. Yeah.
How much slower would a neural network be for inference versus the LDA that you end up using?
I think there will be a noticeable delay according to the subject, but it won't be like so bad that it's not going to work at all. I think it's around 1 second, 0.5 second delay. But for LDA, like the patient never noticed anything, so it's quite responsive. Yes?
How are you incorporating the unlabeled data that you're picking up during use?
How am I incorporating?
Yeah.
Yeah. So as I said, like there's an ensemble of classifier, and each classifier has their own data buffer. So we label this unlabeled data set according to the agreement heuristic, right? And if they agree, we will just add this data sample into the data buffer of the unconfident classifiers. And then once a while, we will update the unconfident classifiers using their own data buffer. Is that what your question is?
Yeah, thank you.
Yeah.
How do you form your data? Like the signals, they are sequential data, right?
Yeah.
So like you do any windowing, or how do you split them? And is there any difference on the way you split them that will affect the results?
Yes, that's a very good question. So we still do like the standardization thing on the incoming unlabeled data, because in the initial stage, we train an initial classifier on the initial data set, right? And from the initial data set, we can infer the statistics from the data set, how we can standardize the data. And we will use the same like mean and standard deviation from the initial training data set to deal with the new incoming unlabeled data. So we do the same transformation.
So what I mean is, do you like do any windowing on the data? Like you split them for every 1 millisecond or 1 second for the continuous signals?
We don't do window on the new data. No. Yeah. But it's coming at 100 hertz. So every second there are 100 new samples. Yes?
How many more features are introduced with the new sensors for the second approach?
How many more new features?
Yeah.
So there are IMU, which gives the pulse I think it's 6 values because it's position plus orientation. There's a pressure, which is a single value, and there's motor position, which is also a single value. So before we have 8 features, 8 channels from the EMG armband. Now we are adding like 8 more, so double the number of features.
And did you try the semi-supervised approach with only the EKG reading?
So try the semi-supervised algorithm with only the EMG?
Yeah.
We didn't, because the intuition is the semi-supervised learning algorithm goes really well with multimodality data. Because if you have a single modality, then when concept drift happens, there's no room for you to play with. But when you have multimodality, when concept drift happens, if EMG is subject to this concept drift, then you can rely on other modality, right? So that's the idea behind the semi-supervision. So yeah.
A lot of the stuff you might was based on software optimization in terms of the model or the data. Are you also looking at hardware-based optimizations to sort of improve the performance of the thing, or like in terms of how it's performing in real time?
Yeah, for sure. Trust me, there are a lot of finger pointing between the hardware and software team. And every time when it doesn't work, I think it's this hardware team's problem. But yeah, there are a lot of work to be done for the hardware side. Like the migration problem, like after you use it for a while, the position of this finger skeleton changes, and then the open is not as pretty as before. Yeah. The other people will be able to tell more about the hardware thing. Yeah, they are struggling, just as struggling as me. Yeah. Yes.
Does using the semi-supervised increase the inference time?
Yes, that's a good point. Yeah.
Does it do it by a lot?
It does, but it not by a lot, but it does because you are running these updates and you are collecting data at the same time, right? So it does increase the. So that's why, like, when we do a demonstration of our system, we still don't use the semi-supervision because it's slower than the supervised version. Yeah, good question. Any more questions? Cool. Thank you, everyone. Thank you for coming.